So what is the trick of the proof? So the first of all is that if B1, B2, BK, Vn, if they are linearly independent, then we are done. There is nothing to prove. If not, then we have to delete. From that the first vector, suppose Vj, which is a linear combination of its preceding vectors. Which we have already observed in the previous theorem, that either they are linearly independent or you will have some vector Vk which can be expressed as a linear combination of the preceding vectors V1, V2, Vk minus 1. So for that reason, since we have assumed that V1, V2, Vn are not linearly independent, so there must exist a vector Vj, and this j is the largest integer for which the scalar was of its preceding vectors. Okay. So now since V1, V2, Vk V1, V2, Vk are linearly independent, then so since V1, V2, Vk are linearly independent, then we must have this j must be greater than k, because Vj has been expressed as a linear combination of the preceding vectors. So that means V1, V2, Vk up to Vj, these are linearly dependent. Now since we have assumed that V1, V2, Vk are linearly independent, so this j, it must be greater than k. That is, V1, V2, Vk is contained in the set of vectors V1, V2, Vk, Vk plus 1, Vk plus 2, Vj. So this one. So the subset left is a set of vectors V1, V2, Vk, Vk plus 1, and so on, Vj minus 1. And since we have deleted the vector Vj, this one, we have deleted that vector from the set V1, V2, Vn. So after deletion of Vj, the vectors left are the set of vectors this Vj minus 1, Vj plus 1, and so on, this Vn, which has n minus 1 elements. elements. And so its linear combinations are contained in W. That we have considered in the theorem, that is W is the linear span of the vectors V1, V2, Vn. Now after deletion, so after deletion of Vj, although this set of vectors V1, V2, Vk plus 1, Vj minus 1, Vj plus 1, Vn. So we can claim that this set of vectors also be equal to the linear span of V1, V2, Vn, that is W. So our claim is that it is actually W. Although we have deleted one vector from the original set of vectors V1, V2, Vn, but still the linear span is same. But what is the reason? Because just if you consider a vector W, so W belongs to capital W can be written as W will be this alpha 1 V1, alpha 2 V2, and alpha 1 V. Okay, and Vj is beta 1 B1, beta 2 V2, and so on, beta j minus 1 Vj minus 1, because we have seen that Vj is the vector which can be represented as a linear combination of the preceding vectors. That is the vectors which are before Vj. And so we get that. So just putting this representation of Vj in the representation of W, we shall get W equal to alpha 1 V1, alpha 2 V2, alpha j Vj, and alpha n Vn. Now we just put the representation of Vj inside the representation of W. We will have, so alpha 1 V1, alpha 2 V2, alpha j, beta 1 V1, beta j minus 1 Vj plus alpha n Vn. So then by doing the normal proceedings, we will have alpha 1, alpha j, beta 1 plus beta 1 V1 plus alpha 2, this is alpha 2, and the second one is alpha j, beta 2 V2 plus alpha j minus 1 plus alpha j, beta j minus 1, Vj minus 1 plus alpha j plus 1, Vj plus 1, and it is alpha n Vn. So we have seen that W has been represented as a linear combination of V1, V2, dot dot, Vj minus 1, Vj plus 1, dot dot, Vn. So that means, so this implies this is a subset of the linear span of V1, V2, Vj minus 1, Vj plus 1, Vn. And this linear span, since these are the vectors which are in a set W. So it is also a subset of W, giving a linear span of uh, these vectors. Now since V1, hello, okay. So since V1, V2, Vj minus 1, Vj plus 1, Vn, these are the vectors that we have considered in the statement V1, V2, Vn. So these vectors will be in the set W, and since W being a subspace, so their linear combinations are also in W. So that means W equals with the linear span of V1, V2, J minus 1, Vj plus 1, and Vn. So it is very interesting to be noted that although we have deleted one vector from the vectors V1, V2, Vn, the linear span that they have built up remains same, although we have deleted one vector from this one. So this proves our claim. Continuing this process of deletion, now we are considering these vectors. So now we are attempting to delete one vector from V1, V2, Vj minus 1, Vj plus 1, Vn. In the same way that we have done for the first case. And continuing this process of deletion of vectors amongst these V1, V2, Vn, we shall obtain a subset of the form which will contain this subset. Although we have deleted one vector from each time for each time, but the set of vectors will contain these vectors V1, V2, Vk, because they are linearly independent. So each time the index will be greater than k. So we obtain, so continuing this process, of deletion, we shall obtain a subset V1, V2, Vk, Vk plus 1, sorry, I don't need Vk plus 1, we should write it as Vi1, Vi2, VIR, yeah, of which subset? The subset will be the set will be a subset of the original set of vectors V1, V2, Vn, whose span is still W. The span will never change, although we have deleted at each time one vector amongst V1, V2, Vn, just by following the idea of deletion that we have considered in the first case. The linear span of the vectors will remain same. So that is interesting. And observe that after deletion, the set we have obtained is this. So this set it contains no element which is a linear combination of the preceding vectors. Because if it has someone, then we will delete that vector and we will get again another set of vectors whose span is again W. So since this is the last stage that we have considered, the deletion has been completed. So this set will not contain any vector which will be a linear combination of its preceding ones. So observe that this set Vk, Vi1 to Vir will contain no vector which is a linear combination of its preceding ones. Yeah. And therefore, by the above theorem, this set must be linearly independent. So by using the above theorem, this set must be linearly dependent, because otherwise it will have again another vector which can be represented as a linear combination of the preceding ones. So this proves the corollary. So this is the statement of the theorem. So that we have proved, that we obtained. So again, I would like to recite this. So B1, B2, Vn are n many vectors in a vector space B, and W be a linear span of the vectors B1, B2, Vn. Now, if V1, V2, Vk are linearly independent, then there exists a subset of V1, V2, Vn, a subset of these vectors, vectors that we have considered. So there exists a subset of these vectors containing V1, V2, Vk, consisting of linearly independent set of elements, and whose linear span is still W. So that is it. Okay. Now, okay. So now I would like to define okay. So a vector space V is said to be finite dimensional. A vector space V is said to be finite dimensional. Look at the definition very carefully. A vector space V is said to be finite dimensional if finite dimensional over F, the field that we have considered, over which V is a vector space. So it's said to be finite dimensional over F if there exists a finite set of vectors, a finite subset of this in V such that V equals with the linear span of this set. So a vector space B is said to be finite dimensional over F if there exists a finite subset S in V such that V equals with the linear span of the finite set of vectors S. So this way we have defined finite dimensional of vector space. And this is a natural definition. Okay. For example, now suppose capital F be a field. Then if you apply Cartesian product to F n times, then it will be denoted by F. Then this is a vector space over F. Then this is a vector space over F. And the important feature of this vector space is it can be generated by finitely many vectors. And suppose you have an example at your hand, a set of n vectors which are and the set of vectors. Suppose the first one is 1, 0, 0, 0. Second one will be 0, 1, 0. So 1 will change 1 place at each time. And the last one is 0, 0, 0, 0, 1. This is here. So this is the nth place. So these vectors will generate the vector space B. That is, their linear span of these vectors will be V. That is, instead of vector this will generate V. That is, V means sorry, F to the power n. That is, F to the power n is a linear span of E1, E2, En, or in general, Ek will be denoted by 0, 0, 0, 1, 0, 0, or 1 is in the unit place. So this is a natural example of finite dimensional spaces. Just considering any field, you will have finite dimensional spaces like this for any n and f. Okay. Now let us have a look at the following statement. Okay. So this is again a corollary of the above theorem that we have proved for finite dimensional vector spaces. So let us suppose B be a finite dimensional vector space over the field F. At each time, wherever you are considered a vector space, you must mention the field. That is very important. Okay, this is a practice actually. Whenever there is no need to mention, but I think you need to mention the field, whatever it is. The vector space over F. Okay. Now let V be a finite dimensional vector space over F. Then there exists a finite set of vectors V1, V2, Vn, which are linearly independent. That is new in this term. which was not there in the definition of finite dimensional vector spaces. We have only defined that there exists a so in the definition of vector space that we have defined, so a definition of finite dimensional vector space over F. So if there exists a finite subset S, we did not mention that this set of vectors will be linearly independent. But the theorem says that if you are considering a finite dimensional vector space over F, then you may construct a set of vectors, a finite set of vectors, which are linearly independent. By means of the previous theorems, whose linear span is V. Is V. The proof of the theorem looks like this. So since V is finite dimensional, so you must have a finite set of vectors V1, V2, Vn, whose linear span is V. So since V is finite dimensional, so there exists a finite set of vectors, suppose V1, V2, Vn, whose linear span is V. Now let us choose a non-zero vector Vk. Let us choose a non-zero vector Vk out of these vectors V1, V2, Vk. Now since Vk itself being a non-zero vector, so it must be a linearly independent set which consists of exactly one vector Vk. So it is linearly independent being a singleton set of Vk, that is this one. So this is itself a linearly independent set. And by the above corollary, so what was the above corollary? That is, if you consider a finite set of vectors V1, V2, Vn, then what will happen? And if V1, V2, Vn are not linearly independent, but you will have a linearly independent set of vectors amongst them, suppose V1, V2, Vk, then there exists a subset of V1, V2, Vn containing those vectors V1, V2, Vk, which are linearly independent and which spans the subspace generated by V1, V2, Vn. So that was the corollary. And using this one, so here this is the singleton set of linearly independent set of vectors, and V1, V2, Vn, if they are linearly independent, then we have nothing to prove. V1, V2, Vn, if V1, V2, Vn are linearly independent, then we have nothing to prove. The proof has been done. If not, then we proceed as follows. So, being a linearly independent set of vectors which is contained in this vectors. So by the above corollary, there exists. So by the above corollary, there exists a subset of V1, V2, Vn containing Vk consisting of which subset? The subset will consisting of linearly independent set of vectors. Linearly independent set of vectors whose linear span is still V. Span is still V. So the above corollary is very much important, and we observed that yes, using that one, we have this corollary that is for a finite dimensional vector space. Okay. So this corollary gives us an important notion. So this corollary says that if you consider a finite dimensional vector space over a field F, then there exists a finite set of vectors V1, V2, Vn, which are linearly independent, whose linear span is the whole vector space V. So this idea provokes us to define a basis in a vector space. But I would like to discuss this notion of basis in a vector space in the next lecture. Okay. আজকে এই পর্যন্তই থাক।